is not virtualizable by, there's the classic definition that you can look up, Popek and Goldberg. The reason it wasn't was that it was possible to extract privileged state in non-privileged operation. The way that VMware used to work on these older processors is they would actually scan code and detect privileged instruction sequences and then dynamically patch them. And I think their patent on that has just expired, not that anyone's interested anymore. To get around that, Intel and also AMD introduced processor extensions in the mid-2000s that actually fixed the issue of being not virtualizable. I'm not actually going to talk about AMD in this presentation, but it's pretty much identical to Intel. All the concepts apply, except it's simpler and some would say better. So the way that Intel VT-x worked is it introduced a set of new instructions. I think there's 7 in total. But the idea is that there's a large memory region that it's used to do a very heavyweight context switch from the host operating system to the guest operating system. It actually has to have a lot of state because it has to be done atomically. There's no way to really do this in software because you have to switch out state that you're actually on. So you need the processor to help you. This area is called a VMCS, which is a virtual machine control structure. They advertise it as being like less than or equal to 4 kilobytes, but it actually has a lot of indirect pointers that hang off it that have a lot of extra state. An example I have here is there's an MSR bitmap, which is the MSRs that will be automatically saved and restored on entry and exit. And the most interesting one for this talk is the EPT pointer. What is the EPT pointer? So EPT is called Extended Page Table. So it's basically a way to translate guest physical addresses into host physical addresses. It's just another indirection. It wasn't in the initial version of VT-x. That was about 2006. This didn't arrive until 2009 when Intel cut over to the Nehalem microarchitecture. The way that it does it, the indirect translation, is that it uses what look to be very similar to Intel paging structures. So just if you were using virtualization before 2009, how did this actually work? So it was very complicated. One of the bits that you can set in the VMCS is to trap when the processor exits the CR3 register. So you would just spoof that every time that they did a read or a write, you would return what they thought it was, but in reality, you were pointing it at your own set of paging structures, but you had to track the guest's paging structures, and then you had to set their pages read-only, so every time they accessed it, it would trap, and then you could update your shadow copy, because all the guests ones are in, they use guest physical addresses, but the processor wants to see host physical addresses. So all this kind of shadowing and trapping and emulation was maybe 5,000 to 10,000 lines of code. There's lots of papers that talk about how much better their version is than the last one. This was way too much for us to bite off when we started on Beehive, and also it's now an artifact of history. Nobody really has these processors anymore. So the way the translation works, when a guest operating system is running, it's still able to use the standard virtual to physical x86 translation mechanism. So the result of that translation from a guest virtual address is a guest physical address, but that's actually what you want to virtualize from a hypervisor's point of view. So then the next stage of translation, which is guest physical to host physical, it then goes and uses the EPT table that's pointed to from the VMCS. Now it sounds like that's just 2 stages, but it's actually kind of an n squared, because when the processor is translating the guest virtual address to a guest physical address, it has to walk guest physical address page tables. Every single one of those guest physical addresses then has to be translated into a host physical address. So it's sort of an n squared algorithm. Now this would not be performant at all, except that at the end of this, a TLB entry is created that maps the guest virtual address all the way to the host physical address. And that's kept in the processor TLB, so as long as you have good locality of reference, it's not so bad. If no mapping is found in the walk of the EPT, the guest operating system exits back to the hypervisor, and that's called an EPT violation exit, or we usually just call that an EPT fault. So when Intel designed EPT, it's sort of like they realized that they'd made a lot of mistakes when they did the first version of PTEs, and they wanted to fix them. So in a way, EPTs are very much like if you wanted to design page tables today rather than for the 386 processor. So they gratuitously changed a number of bits. You can see here the dirty bit is bit 6 in a standard x64 PTE, and if it's implemented in EPT, sorry, in x64 it's bit 6, and it's bit 9 in EPT. There's actually a read permission bit in the EPT PTE which doesn't exist in x64. So what that means is you can have pages marked exec only. I'm sure there's a use for it. I can't really think of one at the moment. And also there was a large number of reserve bits in the x64 PTE, so EPT has started to use some of those. So bit 63 is a new bit that only applies when running a hypervisor, which is suppress virtualization exits. So my guess is that they'll start subsuming bit 62 and down as they want to add more features to this, where the x64 PTE is pretty much frozen in time. For the first generation of Beehive, which we talked about a few years ago at BSDCon, the design target was really logical partitioning as opposed to dynamic start up and tear down of virtual machines or having lots of virtual machines. So the way that we implemented it was we basically partitioned FreeBSD memory at boot time. There's a loader.conf variable called hardware.physmem, which restricts the amount of memory that FreeBSD will use. So when we started the hypervisor, we used all the memory from there to memory that was reported by the BIOS. And we had our own simplistic memory allocator. The EPT mappings were set up statically when we created a guest. It wasn't very user-friendly having to reboot your system if you wanted to run a guest. The one advantage we did get out of that is we could actually use super page mappings in the EPT just to minimize the number of translations that had to be done. To try to make this a little easier to use for people that didn't want to reboot their machines every time they wanted to run a VM, the next change that we did was we statically allocated, we allocated all the memory for a guest when it was created, but we used the FreeBSD VM system to get that memory. We just kept requesting pages until we had enough memory that we needed. The disadvantage of doing that, of course, is that this memory, which can often be large, in multiple gigabytes, is wired for the duration of the virtual machine. It can't be swapped out. So that also wasn't particularly friendly to running large numbers of VMs, but what it did allow us was it increased our user base maybe by 2 orders of magnitude. Having to reboot every time is certainly not something that people really want to do. So the work that was done probably from mid last year and is now in current is we're very similar to how the Unix process model works. Memory is allocated on demand and it's driven by faults, which is exactly how a user process runs. It starts with no memory. The first time memory is accessed, it results in a fault. The virtual memory system will then process that fault and allocate memory. For virtual machines, we currently use anonymous memory and it's backed by swap. So all the usual advantages and disadvantages of demand paging apply, although I think that history has shown that the pros far outweigh the cons. Because EPTs are basically x86 paging structures, FreeBSD already has a module that manages paging structures. That's the PMAP layer. It's been around a very long time in FreeBSD. It's one of the core pieces of code. I think it's considered exceptionally stable. So rather than writing our own version of PMAP, which we would then probably have to do the 20 years of bug fixing, we decided that it would be easier if we reuse that piece of code. The one issue that we had was that the differences in bits that I had on the previous slide meant we had to do some modifications. And also what is meant by a T or B invalidation is actually quite different for a hypervisor than just a normal CPU. The other similarity we saw is that handling EPT faults are almost identical to handling process page faults. And in a similar fashion to PMAP, there's already an existing piece of code that's very well debugged, maintained, very feature-rich, which is the FreeBSD VM code. So rather than writing our own version, we just decided to use the existing VM code. So the way we did it is every process in FreeBSD has a data structure called a VM space. That's where all the memory regions are underneath. So we allocate a VM space for a guest physical address space. Basically starts in 0 and goes up to maximum memory. There's some holes in it, but a VM space is perfectly fine in dealing with that. The one nice feature we have is that there's a routine in FreeBSD called VM fault, which handles page faults for a VM space. So we can actually just call that routine, passing at the VM space, and it will traverse the entire virtual memory system, go and find the backing objects, bring in pages from swap if needed, or allocate them if needed, and set up the mappings using the PMAP layer. So by using this, not only did we reuse code, we also threw out a lot of code of our own that may not have been that great. One of the issues that we face when doing this work is that, like VT-x, it's actually a moving target. Intel are continually adding new features to it with new processor models. In the first versions of VT-x that we were using, the EPT paging structures didn't have support for accessed and dirty bits. And the FreeBSD AMD64 PMAP relies on that. Having hardware support is kind of nice, when you're trying to work out if there's activity on a page or whether it should be swapped out. Usually you want to see whether the page has been referenced or whether it's been modified. Fortunately, Unix has a long history of dealing with processor architectures that don't have AD bits. So I think the classic one is the VAX. From FreeBSD's perspective, MIPS also doesn't have AD bits. So we had a lot of code that we could look at and people that we could talk to that had dealt with this. One of the interesting things we did is that we tested this. Once we put in the support for this, we could actually enable emulation of AD bits for the existing hardware-based x86 paging structures. So that's how we actually did our testing. We just ran up FreeBSD using AD bit emulation and just kind of did a whole lot of tests to verify that that actually worked. And once we'd done that, we were fairly certain that would also work for the guest operating system. One of the issues you have when you basically have an operating system that memory is not accessed at constant speed because it's possibly not wired, it may be paged out to swap or it may not be allocated. You have kind of timing issues. So some of the testing that we were doing was basically flush all the paging entries. Then you would get an interrupt, and the interrupt may take hundreds of milliseconds to actually get the memory that the code that the interrupt handler would run in or the stack that was going to be used for the interrupt handler. I don't think there's a lot that you can really do for this because as a hypervisor you don't really know what guest operating system you're running. I'm sure that there's heuristics that VMware use. You may be able to work out or have a policy to say that maybe the low 4 megabytes is operating system code and you'll just keep that wired. But we had some interesting issues. You get lock timeouts. But basically you'll only see this if you're having massive overcommit and your guest operating system is swapped out. To do I/O in a hypervisor on Intel, you actually have to do a lot of instruction emulation. There's no hardware support for MMIO reads or writes. Our existing instructional emulation code, it gets given a guest instruction pointer, so we have to locate the code at that instruction pointer. To do that, we have to do a software walk of the guest paging structures to locate the code, so then we can read in the instruction to emulate it. Because we're touching a lot of memory, we used to assume, or we were able to assume previously to this work, that memory was all wired. But now it's possible that some of those paging structures might be paged out. So what we had to do was put in a lot of calls to explicitly faulting pages before we access them. That also meant the context that we ran this code in had to be changed so it was in a sleepable context. We used to run this code in a very tight loop from the VM exit, which was actually in a FreeBSD critical section. But because we could fault, we actually had to move that outside of the critical section into normal thread context so we could sleep. At the time, we thought that may hurt performance, but it doesn't seem to be too much of an issue. The other problem that we saw was that we were mishandling some error conditions in VT-x previously, because we were never getting EPT faults on memory access. There was a particular code path that wasn't being exercised. Now all of a sudden, when you go to execute code, you can get a fault because the code page doesn't exist and has to be swapped in. And we had a bug there where we would lose an interrupt that we were injecting, because there's a fairly complicated piece of documentation in the Intel spec on priority of exceptions, and we kind of had it backwards where the EPT has high priority on interrupts and it would delete the interrupt condition. So this first manifested itself as the console would just stop working, and that's because we were losing an interrupt from a character coming in. So it was kind of hard to track down. One of the advantages of being able to reuse the virtual memory system is that we kind of get the features of the FreeBSD virtual memory system for free. So one feature that FreeBSD has is transparent super pages. And that's kind of a combination of a number of pieces of code, but it's all inside the VM system. Basically, we just call VM fault, and then the VM system can do all the work for us. It can go and try to find physical pages that have the same alignment. It'll do contiguous allocations. It uses the PMAP layer to promote 4K mappings up to 2 megabyte mappings and back down again. So we didn't actually have to do any work at all to be able to use transparent super pages. We ran some build wall benchmarks. I think the ARM guys saw the same thing. There's really no difference, but that isn't a bad thing. It just means that all the extra work that you're doing for super pages doesn't make anything worse, just in normal benchmarks. However, if you run a very memory-intensive benchmark, it makes a very large difference. So there's a benchmark that Alan Cox made available to us called GUPS, which is giga updates per second, and it's basically just random walks through memory, similar to the stream benchmark. So we ran this test on just a fairly low-end Haswell CPU. If you give GUPS, we ran a guest, gave the guest 24 gig, the system had 32 gig of RAM. With a 12 gig working set, you basically just run this and then it'll finish at some point in the future. So the combinations were we just enabled super pages in both the guest and the host. When they were both turned off, the benchmark took 500 seconds to complete. Both turned on, of course, it's vastly better because the total table walks just shrink to be super pages on both sides. The middle ones are sort of interesting, and in fact, I'm not sure that we can really explain them. They should be more asymmetric than what they are. The amount of traversal is the same. You have 2 megabytes on one and 4K on the other, and that's just reversed, except that with the way TLBs work, with the combined mapping TLB that I mentioned, which is guest virtual to host physical, that should do the entire translation, where If you have it the other way around and you don't have super pages in the guest, you only have a 4K translation. So you would still have to do that longer walk. So we had expected the numbers in the middle to sort of be further apart, that one should be worse than the other, but they turned out to be sort of similar. So I think we still have some work to do to understand that, but that doesn't actually impact the really good and really bad numbers that we saw. Beehive also supports PCI pass-through. What we have to do for PCI pass-through was program, it's only supported on Intel processors that have an IOMMU or an IOMMU or an external IO hub. So we program the IOMMU to basically have the exact same mappings from guest physical addresses to host physical addresses, because the descriptors that the device is accessing all have guest physical addresses. The physical addresses that are being programmed into the adapter are all guest physical. So they have to be translated in hardware to host physical. So an IOMMU table is very similar to an EPT table. In fact, on Intel, they can just be overlaid on top of each other. The problem is the IOMMU has its own concept of a TLB. It's really not amenable to being changed very quickly dynamically. So basically, what we do when we see a PCI pass-through device is we just wire all guest memory. We fall back to how we used to operate. That may not be optimal, but our excuse is that PCI pass-through was kind of a special case. If somebody's doing that, we assume that they really know what they're doing and they're quite okay to wire guest memory. Presumably, it's done for performance reasons, and if you want to have performance, you probably don't want to be faulting in guest memory at all. So some of the things that we're looking at extending this work, currently we don't really have good statistics on VM space memory usage. FreeBSD has a lot for VM spaces that belong to a process, PS, top, but currently we have a guest VM space is floating. It's not really attached to any process. So it's a little hard for us to actually look in and see how much wired memory is associated with that VM space. The access and dirty bits that we have on the EPT entries, that can be used for implementing live migration. Basically, what you want to do for live migration is move memory from a guest operating system from one host machine to another host machine. So there's sort of classic algorithm is that you just do a loop through all memory. You start copying memory over, and then you mark it as not accessed, and then you keep iterating until all the memory that you've copied to the other machine hasn't been touched anymore. Sometimes that's a little difficult kind of when you get right to the end when there's just small pieces of code that are running, but usually what hypervisors do then is just stop the guest temporarily and just copy the remaining pages over. So the VM system has given us infrastructure that we can use to implement this. Currently we just use anonymous swap back to memory for VMs. That's really not that flexible. In particular, when it comes to configuring swap, I think people really don't care much anymore. They usually don't consider it an issue, but all of a sudden it is an issue for virtual machines. If you want to massively oversubscribe memory, you would have to make sure that there's enough swap to back that. It's probably really not a good idea just to use swap. It's somewhat anonymous. What we probably should do is use a file-backed memory object. What that also allows us to do is if we want to suspend or resume the guest virtual machine, all the memory can just be written out to that file, and when we restart, we can read it back in from that file, or we can just set it up to dynamically page in from that file. So just to recap, one of the advantages of having a hypervisor that's actually integrated into the operating system as opposed to something that you install later is that we get to reuse the subsystems that are inside the operating system. Often these APIs are not exposed directly. By using these subsystems, we can use new features. The example is, with transparent super pages, we didn't actually have to do anything. In fact, if we had have implemented our code before it existed, we still wouldn't have had to do anything because it's part of the VM system. Doesn't really reach down into the lower layers. And also being part of the OS, we can modify these subsystems when we need to. I think if you look at VirtualBox, they have a much harder job because they're not really part of the community. We had to make changes to the PMAP subsystem. Normally that's just considered an area of code that you really don't want people to modify, but we had the support of the maintainers of that subsystem. So we were able to do that. All right. Does anybody have any questions? Paul? Yeah, the question was if I was given a blank sheet to design a CPU to make it hypervisor friendly, would I do anything different? Was that the question? I don't think anybody would design a CPU that looked like an Intel CPU if they were given a blank slate. But despite how ugly it may look, it's actually, it works. It works fast. It's very inexpensive. As complex as VT-x is, it actually works. And that, in the end, that's probably all that matters. The question was, could it be done more elegant, more efficient? I think if you couldn't do it more elegant and more efficient, you would have a problem. It's, the part I mentioned about the instruction decoding, it's just insane. Variable length instructions with bits that depend on other bits and then reuse of prefixes to change the meaning of other bits further in the instruction. I think if you just do a Google search on MIPS emulators, there's just hundreds and hundreds of pages. People can kind of write one in an hour. If you look at fully featured x86 instruction emulators, there's basically two. It's just that complex a job. No, we have a path to get there. One of the shortcuts we took in Beehive is that we didn't do a BIOS. Actually, when we started, there was no 16-bit support in VT-x, so we couldn't really do one anyway. Windows, so also we've never run an operating system that we didn't have access to the source code for. We've always been able to look at what was happening in the guest and correlate that to what we were seeing. So Windows will be the first one that we're going to take on that is just a black box. We'll probably run it in existing software emulators first and instrument them and look at how it's accessing like the local APIC just to make sure that we have the instruction emulation there. Yeah, there's just a lot of little tasks that we have to go to, but that's our goal. We absolutely want to run Windows. I'd like it to be a lot less than a year, but it's still an unknown. It's a dark tunnel. Any other questions? All right, I'll do something unlike the JR line and actually finish early. Thank you.